This winter, my research focused on understanding the role of isotopic composition on the photoluminescent line width of defects in zinc oxide, which will be used to better understand solid-state qubits in zinc oxide. Qubits are the fundamental components of any quantum information processing system. There are many physical systems which can act as qubits. However, the type of qubit of interest to us are electron spin qubits. In this case, we can define electrons in an upspin state as holding a 0 and downspin state as holding a 1. Specifically, we want to use the spin of electrons which are weakly bound to substitutional impurities in zinc oxide. These include gallium and aluminum substitutions. The way we can control the spin of these electrons is by exciting them with a laser while they're at a low temperature and in a strong magnetic field. Before an impurity has been excited, it will sit in a state we call the neutral donor state, which consists of just the positive impurity and the weakly bound electron. These impurities are called shallow donors, as the electron can travel up to multiple lattice sites away from the impurity. If we use the correct laser wavelength and polarization, we can excite another electron, leaving us with 2 electrons and 1 positively charged hole orbiting the impurity. This state is called the donor-bound exciton. The donor-bound exciton must have 1 upspin and 1 downspin electron. Either one of these can recombine with the hole, meaning that we may be left with a flipped electron spin. When this recombination happens, a photon will be emitted which we measure. For a single specific donor, there's a narrow distribution of photons which can be emitted, the width of which we will call the homogeneous line width. However, we actually measure the photons from an ensemble of donors, each of which might have a different average transition energy. The width of this line is called the inhomogeneous line width. This second line width will be affected by variations in the isotopic composition of the environment surrounding different donors, among other factors. One specific application of this research is in quantum memories, which among other things can be used to extend the range of quantum communications. Knowing the inhomogeneous line width will be important in determining the potential of zinc oxide in quantum memories. This is because the inhomogeneous line width effectively determines the memory's bandwidth. The isotopic composition's contribution to the broadening of the inhomogeneous line width has been observed in silicon. Zinc oxide has a wider spread of isotopes than silicon, so we might expect these effects to be substantial. However, these effects still may not be as pronounced as the broadening from factors like temperature or strain. The transition energy between the donor-bound exciton and the neutral donor depends on the average mass of the surrounding lattice sites. How we compute this average is very consequential in the predicted line width. If we compute the average based on a smaller environment, we will get a larger inhomogeneous line width, since including more sites in the average will draw us closer to the overall average mass of natural zinc oxide. Our first guess was to approximate this environment using a hard cutoff, defining the radius of the circle using the known radius of the free exciton in zinc oxide. This led us to a higher than expected value, seeming to imply that the isotopic effects were dominant in the inhomogeneous line width, a result which seemed worthy of more in-depth investigation, especially since the relevant environment should be more complex than a simple sphere. The actual transition energy results from the energy difference of the neutral donor energy and donor-bound exciton energy. If we can model how isotopic effects change these energies, it will tell us the total dependence of the transition on isotopic effects. It seemed plausible that the neutral donor was more tightly bound than the bound exciton, and so contributed more to isotopic effects. Finding the effects on the neutral donor meant modeling the electron's wave function in an isotopically pure environment, then introducing the isotopic effects as a perturbation to the state. To determine this, we found the Hamiltonian for the electron impurity interaction, based on the screened Coulomb potential and central cell correction. Using a plausible trial function and the variational principle, we approximated the electron's wave function. This used the effective mass of a conducting electron in zinc oxide, which essentially approximates the shallowest possible donor. This only provides an upper bound on the neutral donor shift, since the perturbation we used is likely an overestimate. This is because the perturbation included both changes in the valence and conduction bands, while only changes in the conduction band should contribute to the shift. However, the resulting line width seemed more plausible. Further refinement of this model should include the contribution of isotopic perturbation on the donor-bound exciton as well. We had assumed this contribution would be smaller, but upon review realized it's likely significant. More data should also be taken to test this model, including measurement of higher definition line widths and measurement of the line width on an isotopically purified sample. Thanks to Chris Zimmerman, Kai-Mei Fu, and the zinc oxide group for their help and guidance.